Hi, welcome to Points of Topology Live Session 12 NPTEL course. And this is Shobik, and this is the last session for this course for the semester. Okay. So before starting, let me know, do you have any question or any doubt? And also let me know whether am I clearly audible and is the screen visible to you properly or not?
It is screen is visible and audible.
Okay, thank you for confirming. Okay, now let me know, do you have any question or any doubt from previous sessions? Or any questions from assignments or any other doubts because this is the last session. So if you have any doubt from previous sessions or other assignments also please ask. Okay, so if you have any doubt please ask me or else we can start uh, by solving few problems. Note that today's session will be the last session for the semester. So if you have any doubt or any doubt related to assignment or doubts related to concepts, some concepts, please ask me. No need to hesitate because these sessions are meant to clear doubts, solve problems. Okay. So if you have any doubt or any question, please ask me. Okay, since you don't have any doubt and question, so let me start with the solving problems. In between the problem, if you got stuck somewhere or you are unable to understand the explanation of the argument, please stop me and ask. Okay, so let's start the first problem of today. So it will be a 2 hour session. So yeah, so the question is that let x and y be topological space with at least 2 points, and let y be Hausdorff. So now question is that, so first question is that if x is not Hausdorff, then show that there does not exist any continuous function, there does not exist any continuous injective function from x to y. Okay, so this is the first part, and second part is that show that converse is not true. Okay, so let's start the first one only. Okay, so the question is that, so there are two topological spaces x and y with at least 2 points. Okay, and suppose y is Hausdorff. Now question is that if x is Hausdorff, then we need to show there does not exist any continuous injective function from x to y. What does that mean? If this means that if there are two topological spaces x and y is Hausdorff, and both have at least 2 points, then, and if x is not Hausdorff, then what, then x cannot be embedded inside y. Okay, so that's the same thing as this. Okay, now hint is that, so first you should try to think yourself, so that's why I'm giving the hint. Okay, so the hint is the following. um subspace of a house drop is with a house drop. Okay, so this is the hints. House drop is a house drop. Now you try to use this hint and try to solve the part of the given problem. Okay. So for the part A, what it tells if X is a house drop, then X cannot be embedded inside Y. Okay. Now somehow from the statement you need to come up with some subspace of Y, which is violating some condition, possibly house dropness. It is my natural guess, but and that's why the hint I wrote. Now you should figure out mathematically exactly what is happening or how to critically argue it. Okay, please take your time, think about it, let me know. Do you understand the question? I hope you understood properly. So yeah, so please take your time, let me know how to argue this properly. So basically, what you need to show. So the more hint I must give is that show that if there exists injective continuous function, then fx cannot be Hausdorff. Okay. So if there is some injective control x to y, then image of x will be f of x. Now try to show that the injective continuity implies fx cannot be Hausdorff such as a y. Okay. But in general, since y, but sorry, but fx should be Hausdorff. Okay. So now try to think about and okay. So if it should be that's okay, but you somehow now need to prove that fx cannot be Hausdorff. Okay. Think about it and let me know how to show the fx cannot be Hausdorff. Of course, for this you need to use the injectivity of f. Okay. So yeah, try to figure out. Okay, so one. Okay, so so let me explain this. How to show this? Okay, so so let assume. So we are going to use the method of contradiction. So what is the methodology? Methodology will be method of contradiction. Okay, methodology will be method of contradiction. Okay, so so let assume let fx is Hausdorff. Okay, these imply so fx is Hausdorff. Okay, now claim that x Hausdorff. This is what we're going to prove. Okay, proof of claim. Choose x0 x1 belongs to x and x0 not equal to x1. So this implies f of x0 not equal to f of x1. Why? Since f is injective. This implies there exists u containing fx, v containing f of x1. This u and v are open in f of x such that u intersection v is equal to empty. Okay. Since u is open in this, so this u can be written as u prime intersection y, and this v can be written as v prime intersection y. Sorry, v prime intersection. Sorry, it's a typo. V prime intersection if u prime intersection for v prime intersection f of x. Okay. So then this equation tells that u prime intersection f of x intersection v prime intersection f of x empty. This tells what u prime intersection v prime intersection f of x is empty. Okay. Now we are applying the inverse. This implies f inverse u prime intersection v prime intersection f inverse f of x empty. And this whole thing is nothing but f inverse u prime intersection f inverse v prime. So this tells what this implies. F inverse u prime intersection f inverse v prime is equal to empty. And this thing open in what? Open in x, and this f inverse v prime is open in y. Okay. This thing contains x naught, and this thing contains x1. Okay. So this tells what? This tells that so and observe that what we choose initially. Initially we choose 1 minute. Initially we choose x naught and x1, 2 points of x and different. And finally what we got? Finally we got two open sets containing x naught and x1, and the intersection is empty. So this tells what? This implies that x is Hausdorff. But this is a contradiction by the given hypothesis. Okay. So this says that, so this implies f of x cannot be Hausdorff. So this implies f of x cannot be Hausdorff. So that's why this is done. Okay. So now let me know, is it clear to you, or do I need to explain it once again? Please take your time and let me know. I'll send you back with a few minutes. Okay, so now can you please tell, should I re-explain this to you? Okay, I think I should re-explain. Okay, so let me re-explain this 1 minute. Well, so there are two parts of the question. Till now I have only solved the first part. Before going to the next part, let's first re-explain this, okay? Because this is quite tricky. Anyway, so the question is that suppose x and y two topological space having at least 2 points, okay, and y is Hausdorff. The question is that if x is not Hausdorff, then show that there does not exist any injective function from x to y, okay. So, okay. So now what we so as the matter argument, firstly we are assuming that if so first we assume that if it is house, okay. Under the assumption, we are going to show that X is house drop. So how to prove? So in order to show house drop, what we need to show? We need to choose two distinct points which are distinct. I want to show these 2 points can be separated by means of open sets. Okay, that is there exists joint open sets of capital X containing those 2 points x0 and x1, but their intersection is empty. Okay. Now, since f is injective, this tells that f of x0 not equal to f of x1. Okay. Now we have assumed that f is a house drop, so there is an open set U, which is open in fx, and an open set V, also open in fx. This U containing f of x naught, V containing f of x1, so the U intersection V empty. Okay. Now by means of subspace topology, U is open in fx. This tells that U prime, that U considered as U prime intersection. 1 minute, please. There is some issue with the software. 1 minute, please. Okay. Now, by means of open sets that U can be written as U prime intersection f of x, and V can be written as V prime intersection f of x, where this U prime, okay, I must write this, where this U prime and V prime are both open in where Y, okay. Now, this equation U intersection V empty, this thing gives U prime intersection fx with intersection of V prime intersection fx empty. And this tells that U prime intersection V prime intersection if X is empty. This is nothing but the basic set theoretical argument. There is nothing to explain. So now we are applying F inverse both sides. This tells that, and now inverse always behaves at intersection very well. So this tells that F of F inverse U prime intersection V prime intersection F of F inverse F of Fx is empty. This tells that F inverse U prime intersection F inverse V prime this is equal to this, and this tells that f inverse u prime intersection f inverse v prime empty with the points containing x naught and x1, and if inverse u prime is open in x, if inverse v prime is open in y. Okay, so this states that x is house drop, and this contradicting the hypothesis. This states that fx cannot be house drop. Okay, so that's what the argument is. Okay, I hope now it is clear to everybody. Now, uh, no, we need to now show the converse not true. That is, okay, so think about part B. In part B, what we need to do what? Construct an example of injective continuous map F from X to Y such that X house drop and Y not house drop. Okay. So in this type of example you need to construct. Okay. Think about it and let me know. You need to construct on the example. There is nothing to prove. You need to construct some examples or some functions which is continuous as well. I did not. I have mentioned. Okay, continuous injective functions so that the code so that domain is house drop but codomain is not house drop. Such example you need to construct. Okay, take your time. Think about it. Okay. So are you able to construct the counter example for this
Yeah,
part?
can you explain the part one?
Okay, sure.
What part A?
Okay. Okay, and so yeah, so this the previous part is quite tricky. So let me re-explain this. Okay, and in between, if you have any doubt or any confusion, please stop me and ask the question. Okay. So the given hypothesis that x and y are two given topological spaces with at least 2 points and y is Hausdorff. Okay, and suppose x is not Hausdorff. Now we need to show that there does not exist any continuous injective function from x to y. Okay, sorry. So for that, what we are doing is that we're trying to show that if such a continuous function exists, then f of x will be Hausdorff. Correct? But we claim that this f of x is Hausdorff. This will imply that x will be Hausdorff. Okay. So in order to prove this, but this should not be the case according to hypothesis. So now we are going to prove that x is Hausdorff. Okay. So we are choosing in order to show something is Hausdorff. What are we doing? We are choosing 2 points x not an x1 such that x not equal to x1 and f of x not equal to f of x1 because since x f is ejective. Okay. Now since f of x is Hausdorff, so this tells there is this open sorry there is open set U containing f of x naught, open set V containing f of x1. Okay, and such that this U is open in f of x, the V is also open in f of x, such that U intersection V is empty. Okay. Now by the subspace topology, this U since U is open in f of x, so this U can be written as U prime intersection f of x, and this V can be written as V prime intersection f of x. This U prime and V prime are both open in Y. Okay. So now this equation U intersection V equal to empty, this equation gives what? 1 minute. What is this? Okay.
Ah,
Okay.
yes, I understand.
Okay. So yeah. So till now, is everything clear to you?
Yes,
Okay. So now, so this is the first half of the first problem. Now for the second half, since U intersection V is empty, so this states that U prime intersection V prime intersection f of x equal to empty. So this now we are applying f inverse both sides. This states that f inverse U prime intersection V prime is empty, and this states that f inverse U prime intersection f inverse V prime is empty. This F inverse U prime is open set in X and F inverse Z prime is open set in Y. The both contains X not X respectively. So this tells that X is Hausdorff. This is contrary to the given hypothesis. So that's why F of X cannot be Hausdorff space. Yeah, so that is the argument. So is the full argument clear to you? Uh,
yes, yes,
okay, thank you for the confirmation. Okay, now for the part B, what you need to do, you need to construct an injective map F from X to Y for this part B. You need to construct an injective map F from X to Y such that X is Hausdorff and Y is not Hausdorff. Okay. Take your time, think about it, and try to construct such a counterexample. Okay, it will not be very difficult, but think about it. Okay, so are you able to figure out the counterexample? So it should be tricky. Please unmute yourself and tell me if you found. No problem if you're unable to found. If you get some kind of partial idea, that is also fine. So do you get any kind of idea, or at least any guess how which type of counterexample might work? Okay, so let me write 1 minute. Okay, so what we're doing is the following. We are considering x to be r. 1 minute, please. We are considering x to be r with usual topology. Seems that there is issue with the software. So let me restart it. Okay, please wait a moment. So we are considering x equal to r with a usual topology. Okay, this is the first thing, and we are taking y to be r, y to be same r with discrete topology. Okay, so one the issue the software itself has some understanding. Kindly hold a moment. And we're taking f to be we are taking f to be x to y, that is to x goes to x identity map. And check that and check that check other conditions, check the other conditions are not getting satisfied. Okay. And check that other conditions are not getting satisfied. Okay. So, so this is the first part of this problem. So for second part, what you have done? We choose X to be a visual topology and Y to be a discrete topology and AFX to Y excited. We are checking that other condition not getting satisfied. Okay. That is domain, Hausdorff, but not codomain. Okay. So this is the first problem. So let me know, do you have any doubt, any question, the first problem, or else we shall move for the second problem on itself. If you have any doubt in the first problem, then we can discuss again, else we can move for the second problem itself. Okay, so it seems that you don't have any problem, and it seems this problem is clear to everybody. So now let's go for the next question. Question is that let q from x to y be closed, surjective. Let f of x to y be closed, surjective map such that Q inverse y is compact for all y in y. Okay, now show that if x is regular, then so is y. Okay, so first let me explain. Qx to a closed surjective and Q inverse y compact for all y. Show that a y regular. So basically, what you need to do, you need to basically explore the definition. That is the only hint. There is nothing to give extra hint. Exploit definitions only. Okay. So what does it mean regularity? By regular space means what? If you take any closed set, any point non-containing that's not inside that set, there are two open sets which are disjoint containing that point and containing that closed sets. Okay. This is by what we mean by uh, regular sets, right? So you need to explore definitions only. That's all. So try to figure out, think about it. It is not easy, but it is not very difficult. It's quite tricky. Please try to figure out by yourself. Then I shall explain. Okay. Please take your time and let me know. Okay, so now, so are you able to figure out, Mustafa? At least, can you please explain for how to start this problem, or do you get any kind of idea? At least, how what is the main trick? Are you able to catch it? Please unmute yourself and let me know. Okay, so let me re-explain this. Sorry, there is something wrong. I don't know. Okay, so given y belongs to u subset of y. Okay, kindly hold a moment, please. There is some problem with the whiteboard, I guess. It's not properly synchronizing, so that is a big problem, I think. Kindly hold a moment. Okay, so let me write it down. Hmm. So given y belongs to u subset of y. Okay. So given y belongs to u subset of y, where this u is open in y, consider f is equal to q inverse singleton y, which is subset of v. Okay. Which is nothing but q inverse of u. We are denoting it like that. Okay. Now, now, by regularity of x for each x in f subset of v, for each x in f subset of v, we to get an open set, to get an open set v suffix x such that X belongs to Vx subset of Vx closure subset of B. Now by compactness, now by compactness of if we get what? We get infinitely many xi's belongs to F such that F subset of union of Vxi this is equal to W. Now since this Vxi is finite family, okay, 1 minute please. Is there an issue with the internet? I don't think so. But since Vx a finite family, we can put W prime is equal to union of I Vxi closure, which is subset of P. Okay, now since Q is closed map and K is equal to Q of W closure, which is a closed subset of which is a closed subset. Okay, this tells that Y belongs to K subset of Q, and we claim K is a neighborhood of Y. And for this, we are doing for this 1 minute, please. Hmm. Ah, for this, what does this time will do? Okay, so for this, uh, for this, consider the closed set intersection I x minus bxi subset W closure, and it follows that H is equal to Q of intersection I x minus vxi subset of k, and H is closed in Y. This implies G is equal to Y minus H is open, and this tells that Y belongs to G subset of K. This tells Y belongs to G subset of K, and this implies this proof is done. So let me re-explain. I understand that this proof is very much tricky. That's why let me re-explain. Okay, I select back to 1 minute. Okay, please go through the argument once. I select back to 1 minute. Okay. Okay. So so let me re-explain the argument here. Wait a minute.
Can you repeat? the previous argument.
Okay. Okay. So, can you please tell me that whether should I repeat the whole argument or you are particularly asking for any part of the argument? Should I repeat the whole argument or you are interested to understand the specific part of the argument, Mustaq?
Huh?
Should I repeat the whole argument or should I or are you or do you want to understand a specific part of the argument or the whole argument?
Basic part.
Okay. Okay. So as per the hypothesis states that there is a map from Q x to y which is closed and surjective map says that the inverse image singlet is a compact. Okay, and under this assumption, we need to show if x is regular, then y is also regular. Okay. Well, the argument which I gave is nothing but the exploiting the definition only. But I must admit that this the way of proof is quite tricky. It is not straightforward. Although it is not difficult, but not straightforward. Okay. So now let me explain the argument. So we choose a y from U containing a subset of y. Okay, and this U is open in a y. And we are considering let capital F, which is nothing but Q inverse of 1. Which is nothing but Q inverse equal to y subset of V is equal to Q inverse of U. Now, by regularity of x, for each x belongs to V, we get an open set Vx as that x belongs to Vx subset of Vx closed subset of V. Y by definition. Okay, there is nothing to write. So now, by compactness of F, we get a finitely many xi's in F such that F subset of union of Vxi. Now, since V of xi is finite family, then this tells the W closure is equal to union of I V of xi closure subset of V. Now, since Q is closed map and K is equal to Q of W closure is a closed set, this tells that Y belongs to K subset of Q. Now we claim that K is a neighborhood of Y, and for this, consider the closed set intersection of x minus vi subset of w closure. And this tells that if we call the h to be the q of this whole intersection, this h should be closed. And if we take g to be y minus h, then y belongs to g subset of k. And this so yeah, and so that's why this tells that y regular. So that's why we are done. I don't understand, Mustaq.
Yes.
Okay. So now let's go for the next question. Let G be a finite group acting on a Hausdorff space X. Then show that the orbit space X divided by G G is a finite group acting on Hausdorff space X. We need to show that X divided by G is Hausdorff. Okay. So now So I mean, look, the point is that here also you need to explore definitions. So you need to start with distinct points x, y, x in the from the question space and try to figure out that any two points can be separated by disjoint open sets. Okay, so think about and take your time. And basically here also you need to give exploitative argument by choosing the points and go along the definitions. Okay, so take your time, think about it, and let me know. It is not. It is a more. It is more or less easy. Okay, just you need to think about and write down the argument accordingly. So please take your time. As will be after 1 minute. What happened? Okay. So, okay. Hmm. So, okay. So, Mustaq, can you please unmute yourself and tell me what do you have any guess or idea of this how to proceed? Mustaq, can you please unmute yourself and let us know that how you can proceed? Okay. So let me explain this. One. Okay. So, hmm. So, so, so suppose third bracket X and third bracket Y, this belongs to X by G, and suppose this third bracket X not equal to third bracket Y. Okay, this implies what? This implies G of X intersection G of Y is equal to empty. Correct? Now, since G is a finite set, G is a finite set, so Gx, Gy are all finite set. That is obvious. This is finite sets. Okay. Now since X house of, so there exist mutually disjoint family of open sets EY, each containing exactly one point from GX union GY, and by taking intersections intersections from this, we can obtain two open sets. Sorry, what are two open sets? Just two open sets U and V, such that G of U intersection G of V is equal to empty. And now it follows that now it follows that Q of G, so now it follows that Q of G of U and the Q of G of V are disjoint open subsets of Y containing Gx and Gy respectively. So basically, what is the argument is telling? What? Please hold a moment. So basically, one minute, please. Okay. So basically, so suppose we have 2 points. We suppose we have 2 points x and y from x divided by g. Okay. And suppose those 2 points x and y are not equal. Okay. So this says that gx intersection gy is equal to empty. Now since g what now since g is a finite set, so gx and gy are all finite. Now since x is a house drop, so there is a mutually disjoint family of open sets ui, each containing exactly open from gx union gy. Okay. And by taking intersection from this, we can also obtain. So, 1 minute. Hmm. So, yeah. So, GX intersection. Okay. So, now since G is finite and now since X is a house drop, so there will exist mutually disjoint family of open sets UI, each containing exactly 1 point from GX to. That means what? Diagrammatically. Suppose these are big X, okay? And suppose these are distinct points. So this condition tells we shall get open balls U1, U2, U3, U4, U5, U6, all are mutually disjoint. So these are all mutually disjoint, okay? Now, mutual disjoint family opens as UI and each containing exactly 1 point from GX union J. By taking intersections from this, we can also obtain two open sets UV such that GU intersection GV is equal to empty. And it follows that GQ of GU and Q of GV is giant open subs of 1 containing GX and GY respectively. Okay. So yeah, so this is the argument. So is this argument clear? Please take your time. Let me know. Is this argument clear? Is this argument clear to everybody? Mustaq, is this argument clear to you? Okay. I hope this argument is clear. So now, let me. Okay, not this. So the next question is. Okay. So now, if till now everything is clear, and so now if we can move on to the next question. So the next question is as follows. Well, so the next question is as follows. So show that every metric space is normal. Show that every metric space is normal. So for this, what I need to do? One moment, please. Every metric is normal. So in order to do what you need to show, that is to show if we take two closed sets f1, f2, closed sets such that f1 intersection f2 empty, then these two closed set can be separated by open subsets. Okay, so yeah, so this is what it to show. Okay, yeah, so that's what you need to show. So yeah, so think about it and let me know. So it should not be very difficult. So what you need to do, we need to start with some two open to close sets f1 and f2, and then you need to somehow come up with some open. So let me give you. So yeah, so first think about it, then I will give you the idea. Okay, please take your time and think about it. Okay. So, so okay. So let me explain. So the argument goes as follows. Okay. One minute. So let's call the xt be the given metric space. Given metric space. Okay. And let A and B be two disjoint closed sets in X. Okay. And what we need to do, we need to produce disjoint open sets U V such that A subset of sorry A subset of U and B subset of U. Okay. Now what are doing? Now you are considering the distance DAB. We consider distance, that is distance between A and B. Okay, in case you forgot the definition, let me write it down. Distance between A and B is nothing but infimum of distance between a pair of points from A and B. It is called the infimum. That is, if A is this and somehow B is this, then the distance will be infimum for all distance. Okay, so this is what by distance mean. Okay, now that's not important anyway. Now we are putting U to be union of X belongs to A B D A B by 3 of X and V to be union of X belongs to B V of D A B by 3 of X. Okay. Now since U intersection V is equal to empty because of the following reasons. So let Y belongs to intersection P. This implies Y belongs to the open ball of radius dAB by 3 of A. Intersection open ball of radius dAB by 3 of intersection B. 1 minute. For some A belongs to A and B belongs to B. Okay. Now by triangle inequality, D of AB less than equal to D of AY plus D of BY. This is less than equal to 2 times of D of AB by 3. So 2 times D of AB anyway by 3. So, and that's not possible. That's obviously not possible. That is not possible, obviously. Okay, 1 minute. So, so that is obviously not possible. So this tells that U intersection V must be empty. That is, U intersection V must be empty. So is this argument clear? So basically, let me re-explain. Anyway, this is very easy, but I must explain this also because this is quite tricky also. Okay. Okay. So one minute. So basically, we need to show that matrix space is normal. So for that, what we are doing, we are so for that, what we're doing, we are considering to close sets F1 and F2 such that F1 intersection F2 is empty. Okay. And now we need to show these two closed sets can be separated by open subsets. Okay. Now we are assuming that 1 minute. 1 minute, please. Okay. Now, now we are considering the distance DAB between the point between the spaces A and B. And DAB is defined by infimum of DAB, A belongs to B belongs to. We are putting U to be a union of open balls of X between the distance of radius DAB by 3, okay, and B to be in the same way. Now, we are now U intersection B must be empty. Okay, why? Because why the U intersection must be empty? Because if let Y belongs to U intersection B, then Y belongs to B of DAB by 3 of A for some A belongs to A and B belongs to B. Okay, for some A and B. Now by triangle inequality, D of AB less than equal to D of AY less plus G of B. This tells that less than equal to 2 of D times A plus B by 3. This tells that 2 of D times A by 3. This tells this situation is obviously not possible. This tells that even the second V is empty. So yeah, so this is the argument. So this implies that matrix is normal. Metric spaces are Normal, okay. So, do you have any doubt or any question? Please ask. Do you have any question, please ask, or we shall go for the next problem itself. Okay. So, since it seems that you don't have any question or doubt, so we shall go for the next question. Okay. So, 1 minute, please. Um, okay. So, 1 minute. So, the next question is, hmm. So, next question is, if X and Y are topological spaces, then D of A cross B is equal to D A cross DB. This is true or false. I mean, of course, if you must have seen this expression D of A cross B. So point is that you need to basically prove this is equal to boundary of A cross B union A cross boundary of B. Okay, you need to prove this, and you need to provide a counterexample of that. Okay, also give a counterexample for that. So please take your time, think about it, and let me know. So basically, you need to prove that equation, and also you need to give a counterexample. So please think about it, let me know. So look, first of all, in so but what so what is the okay? So first, let me explain. So what is the definition of boundary of A? Boundary of A is not, first of all, boundary of A is not necessarily a subset of A. Okay, so for boundary of A, this thing is yeah, boundary of A contains those elements of capital X. Okay, so boundary of X contains those elements of capital X such that, 1 minute. So boundary of X contains those element of capital X such that that X that any neighborhood of that point contains a point of X along with the point of along with contains the point of X minus. Okay. So that means let me write it down. 1 minute. So this tells that the definition of boundary is that X belongs to boundary of A implies for any neighborhood U of X, U intersection A non-empty, and U intersection X minus A, both non-empty. This is the boundary definition. Okay. Anyway, so yeah. And also this one, and this is equivalent to saying the boundary of A is equal to A closure minus A interior. Okay. So now what we can do is the boundary of A cross B is equal to A cross B closure minus A cross B interior. Okay. So this is what A closure cross B closure minus A cross B interior. Okay. Now, now you can write this thing is equal to A closure minus A cross B union A cross B minus B closure minus B interior. Okay. So it is a matter of basically set theory how just a set theoretic argument will work. So this is a boundary of A cross B union A cross boundary of UK. Hmm. And this tells, yeah, so this is what. Now for counter what you can put, we can put x equal to y is equal to r and a is equal to b is equal to third bracket 0 1. Then we can check that boundary of a cross b is this thing is not equal to boundary of A cross boundary of B, okay? Because this boundary of A cross B is what? Only this boundary portion. But this boundary of A cross B is equal to 0, 1 cross 0, 1. So this is obviously this is not equal, okay? There is no doubt in it, okay? So yeah, 1 minute, please. Okay, so that's all for today. And best wishes for your final exam, which is knocking at the door, yeah, possibly in the, yeah, which is very soon, I guess. So please do solve all of the exercises that we have done in the class till now, and also try to practice all the assignments, okay? And if you have any doubt, you can drop an email to me without hesitation. I shall get back to you as soon as possible. And also remember one thing is that in topology, the more you practice, the more you will be accurate. Okay, so please do not think that okay, I can. So don't think like that it is easy for exam. Don't think like that. The point is without practice, the topology will be difficult. Okay, so please do practice as much as you can. So that will be better, I guess. Okay. So best wishes for your final exam, and yeah, so all the best. Try to achieve maximum of the exam, and I'm the leaving the session. Thank you.